At this point, we've seen two ways to build a data structure that can hold multiple copies of data of the same type, the array and the array list. We haven't talked about Arraylist in a while, even though it was the first array-like thing we studied. Recall that Arraylist did something that arrays cannot. It automatically resizes itself. This is a very handy feature, so you might think that we should always use Arraylist. You may have wondered why we bother to study arrays at all when we have something as wonderful as an array list available. Well, in programming, you don't get something for nothing. While automatic resizing is a very convenient feature, it's not free. As you've probably guessed from the name, an array list contains an array. The array inside the array list has a size that's fixed at construction, just like every other array in Java. The array list works around this constraint to create the illusion that the size of the array is changing by reallocating a larger array when it needs one and copying the existing data to it. If those operations sound expensive, they can be, particularly when the array is large. This is a great example of hiding the details of how a class works so successfully that you don't realize what's happening behind the scenes. There is another hidden expense of the array list. You may have noticed that when we create an array list, we can't say array list of int, but have to say array list of integer. The integer class is called a wrapper class because what it does is conceal one primitive data element, int, inside a class structure. Why we have to have wrapper classes is the kind of thing you'll learn in more advanced programming classes. Even if the class itself took no additional memory, the array list is storing an array of references to integer objects. Compare the memory use of the array primitive array to the array list of integer object array in the memory diagram. In square brackets, primitive array equals new int of 5, array list of integer object array equals new array list of integer of 5. For int I equals 0, I less than 5, plus I, primitive array of I equals I, object array I of I. This is actually adding an integer object to the object array. In most computers, the reference is about the same size as the int value. So we've at least doubled the amount of storage space that the array will take by using the array list instead of the array. In many applications, this won't make any difference at all. But if memory is limited or the arrays are extremely large, this can be a problem. The main debugging problems that occur when using arrays are off-by-one bugs. If you've been doing the assigned exercises up to this point, you've undoubtedly created an OBOB or two by now. Some OBOBs are easier to find than others. For example, going one too many positions in an array is usually pretty easy to find because Java will stop your program right then and there. Going one too few positions in an array is a much harder problem to discover, particularly if you don't test your code carefully enough. Suppose that I've asked you to create an array with 10,000 random integers between 0 and 100,000. Is the code below correct? Final int size is 10,000, final int range is 100,000, int square brackets random equals new int of size. For int I is 0, I less than random length, plus I, random of I equals int math random times range. The loop looks great. It uses the Java idiom where you start the index at 0 and stop with less than the array length, and that usually works. And if you run the program, everything will look just fine. The data will be random enough, the array will be full but not overflow, but everything is not fine here. Even if you ran this program over and over, you might not notice that the value 100,000 will never be chosen, as it was supposed to be. Remember that math.random returns a value between 0, inclusive, and 1, exclusive. So think of the largest value as 0.999999999. When this is multiplied by 100,000, it will be 99,999.999. The incast will truncate this to 99,999, and we're off by 1. So how do you discover a problem that is this subtle? A great trick is to change the constant range to 10 instead of 100,000. If you print 100 elements in the array, you'll quickly see that there are no values of 10, and you'll find the mistake. When we're creating test data, we need to be sure to test every possible boundary condition we can think of. Suppose we'd written a binary search method. We should check that the first element in the array can be found. We should check that the last element in the array can be found. In fact, we could write a test that checks every item in the array can be found, just like the test below. Int square brackets data equals 1, 3, 5, 7, 9, 11, 13, 15, 17. For int I is 0, I less than data.length plus plus I. If my class.binary search of data for data of I is not equal to I, system error print line, element I in the array was not found. Is that enough testing? Well, no. We haven't tested to see that things that are not in the array are not found. Let's add the test below. With the data we've chosen, this test will see that the values that are between every pair of values are not being found when they're not there. For int I is 0, I less than data.length plus plus I, if my class binary search of data of I plus 1 is greater than or equal to 0, system error.println, the binary search is finding things that are not in the array. This is much better, but it's still missing an important case, data that's smaller than the first element. And of course, as always, we should select all this test data before we begin writing the binary search method. Would it make sense to test what happens if the array isn't sorted? Well, not really. Binary search only makes sense on sorted arrays. Another boundary condition to consider is what the code should do if the array is of length 0. Sometimes a 0-length array doesn't make sense. For example, what would the maximum of the values in a 0-length array be? It's hard to think of any value that would be meaningful, so it's best to add a sentence to the Java doc for the method saying that the array must be of length greater than or equal to 1. But sometimes a 0-length array does make sense. For example, a 0-length array can be sorted and searched just fine. Sorting should produce the same 0-length array without breaking, and searching should return false, since there will be no values found in a 0-length array. Try to make your methods handle as many of these special cases in simple, elegant, and thoughtful ways as possible. In a similar vein, arrays of length 1 are also an important special case to consider. In most cases, an array of length 1 is meaningful. There is a special case that we don't usually consider, an array that has not been constructed. If someone asks you to search a null pointer, there isn't much you can do, and frankly, when the program fails, it isn't your fault. We don't usually document the fact that the program will fail if you give arrays of objects that haven't been constructed, since this is considered blatantly obvious. One good place to look for good examples of how programs are tested is JavaBat and Turing's Craft. The test cases that are in the tables on the right-hand side of JavaBat show you how an expert programmer chose to test the code, although they don't show all of the cases that are tested. Think about why each one of these cases was chosen, and you'll learn some of the tricks of the testing trade. The code that generated the test table was supposed to return true if the array had 6 in either the first or last place. Would you have chosen this many test cases? If not, you probably didn't test your program enough. Notice the table didn't test the 0-length array, although that might have been tested in other test cases. I would have tested that case. Now that we've discussed mistakes that are often made implementing programs with arrays, let's talk a little about common mistakes when designing programs. You've probably heard that when you have a hammer, everything looks like a nail. Well, when students first start to program with arrays, they tend to make everything an array. So let's look at a couple of cases where arrays shouldn't be used. Suppose you want to find the number of times a given hashtag was used in a file of tweets, 1 tweet to a line. You could store the tweets in an array, and then you could search the array for the hashtag. You could even sort the array and then use binary search to find the hashtag. That's great programming, right? Well, not really. You could just read in the tweets one at a time and keep a count with a running sum. No array, no sorting, no binary search. As a general rule in programming, you want to keep everything as simple as it possibly can be. One loop almost always beats adding in all sorts of unnecessary bells and whistles. Another place where arrays should not be used is to store data that is superficially all of the same type, but not really homogeneous. For example, we don't usually store an address as an array of strings, since a person's name, street address, city, state, and zip code aren't really all that similar, even though they all could be represented as strings. If we did use an array of strings to hold an address, what exactly would address of 3 mean? Is that the city, the second line of the street address, or something else? These subtle and important distinctions will become more obvious once we've seen the next way to organize data, the class.